sklearn, linear model, Bayesian Ridge. A detailed explanation. Introduction. The Bayesian Ridge class in scikit-learn implements Bayesian linear regression with regularization. This approach combines the strengths of both traditional linear regression and Bayesian statistics, offering robust and flexible predictions. Key concepts. Bayesian inference. Bayesian Ridge regression uses Bayesian inference to estimate the model's parameters, weights and intercept. This means it considers the prior belief about the parameters and updates this belief based on the observed data. This allows BER to handle overfitting and incorporate prior knowledge about the problem. Regularization. Like other regularized linear models, e.g., ridge regression, BER includes regularization terms to prevent overfitting, which can occur when the model learns the training data too well and fails to generalize to new data. This regularization helps to shrink the coefficients towards zero, reducing the complexity of the model. How it works. Prior distribution. BER assumes a prior distribution over the model parameters, which reflects the initial belief about their values. It uses Gaussian priors for both the weights and the noise precision, the inverse of the noise variance. Likelihood function. The likelihood function describes the probability of observing the training data given the model parameters. Posterior distribution. By combining the prior distribution with the likelihood function, BER calculates the posterior distribution of the parameters. This posterior distribution reflects the updated belief about the parameters after considering the data. Prediction. BER makes predictions by averaging over the posterior distribution of the parameters. This provides a more robust prediction than simply using the maximum likelihood estimate of the parameters. The Bayesian Ridge class in scikit-learn offers several parameters to customize its behavior. Int. Default 300. This parameter sets the maximum number of iterations for the optimization algorithm. The optimization process iteratively updates the posterior distribution of the parameters until convergence. Toll float. Default 1e-3 defines the tolerance for the stopping criteria. The optimization process terminates when the change in the estimated parameters falls below this tolerance. Alpha 1 float. Default 1e-6 shape parameter for the prior over the noise precision. A larger value for alpha 1 indicates a stronger prior belief in a lower noise level. This parameter influences how much weight is given to the noise term in the model. Alpha 2 float. Default 1e-6 scale parameter for the prior over the noise precision. The combination of alpha 1 and alpha 2 defines the overall shape of the prior distribution for the noise precision. Lambda 1 float. Default 1e-6 shape parameter for the prior over the weights. A larger value for lambda 1 indicates a stronger prior belief in smaller weights, which encourages regularization. Lambda 2 float. Default 1e-6 scale parameter for the prior over the weights. The combination of lambda 1 and lambda 2 defines the overall shape of the prior distribution for the weights. Compute score bool. Default false indicates whether to compute the log marginal likelihood at each iteration. This can be helpful for monitoring the convergence of the optimization process. Fit intercept bool. Default true determines whether to include an intercept term in the linear model. Normalize bool. Default false specifies whether to normalize the training features before regression. Normalization can improve the numerical stability of the optimization process and lead to better performance. Copix bool. Default true indicates whether to copy the input features X or overwrite them during processing. This can affect memory usage and performance. Attributes. After fitting the model, The Bayesian Ridge object acquires several attributes. Core array like the estimated coefficients for the linear regression problem. Intercept float the independent term in the linear model. Sigma float the estimated noise standard deviation. Lambda float the estimated precision of the weights. Alpha float the estimated precision of the noise. Scores array like the log marginal likelihood at each iteration. Only available if compute score was set to true. Methods. FitX. Y fits the model to the given training data. PredictX makes predictions using the fitted model. Score X. Y returns the coefficient of determination R2 of the prediction, which measures the goodness of fit of the model. Get paramsdeep true returns the parameters of the estimator. Set paramspams sets the parameters of this estimator. Advantages of Bayesian Ridge. Regularization reduces overfitting and helps the model generalize better to unseen data. Robustness predicts by averaging over the posterior distribution of the parameters, making it less sensitive to outliers and noisy data. Prior knowledge incorporation allows the inclusion of prior knowledge about the parameters, which can improve performance in specific scenarios. Uncertainty quantification provides estimates of the uncertainty in the predictions, which can be useful for decision making. Disadvantages. Computational cost. The Bayesian inference process can be computationally more expensive than traditional linear regression. Parameter tuning requires careful parameter tuning to achieve optimal performance. Conclusion. Bayesian Ridge in scikit-learn offers a powerful and flexible approach to linear regression. It combines the benefits of Bayesian inference and regularization, providing robust and reliable predictions while incorporating prior knowledge and quantifying uncertainty. It is a suitable choice when facing overfitting or when prior information is available, although it may require more computational resources than traditional linear regression methods.